Welcome to Maths with EJD. Now I am making this video to show you the Python code for the cost minimization problem we solved. A hospital kind of decision that we solved graphically in the previous video. So here is the Python code, like I always like to do. So again, the question is that a hospital needs to decide on its daily order of two types of medications, Med A and Med B, to minimize costs while meeting patient needs and staying within storage and budget constraints. Each unit of Med A costs $5 and each unit of Med B costs $8. The hospital must order at least 80 units of medication in total each day to meet patient demand. However, it can store a maximum of 120 units of medication daily. Additionally, the hospital has a daily budget of $700 for ordering these medications. How many units of Med A and Med B should the hospital order to minimize cost while satisfying these requirements? That's the problem statement. And then the mathematical representation is in the next cell. So, each unit of med costs $5 and med A costs $5 and each unit of med B costs $8. And that is why oh, sorry, this is a minimization problem. So it should be minimize. So this should be minimize, right? We are minimizing because the objective is how many units of this should the hospital order to minimize cost. So we have to minimize Z equals 5. So if X, for instance, I used A and B when I was solving graphically. So here I'm using X and Y. So you are very free as far as you know that X is the number of the units of med A and Y is the units of med B. That's all. So if 1 unit of med A is $5. So if you order 8 units, if you order X unit, that means you are going to spend $5X on med A, and then you spend $8Y on med B. So we are minimizing that cost. So we are minimizing that cost, on med A and med B with that combination. Then the hospital must order at least 80 units of medication in total each day. So it means that the so if you order, so whatever units of med A plus whatever units of med B you order should not exceed 80 units. Should not be less than 80 units. Sorry, that's at least 80 units. That's greater than or equal to 80 units. So that's one constraint. The other constraint is, however, it can store a maximum of 120 units. So maximum of 120 units means that the accumulation of both medications should actually be not more than 120, because if you get more than 120, the hospital cannot store it. So that's why we have the second constraint, which is X plus Y is less than or equal to 120. Then additionally, the hospital has a daily budget of $700 for ordering this medication. So whatever you do, you cannot spend beyond $700 in ordering either medication A or med A or med B or both. You cannot spend more than $700. That's why the third constraint is 5X plus 8Y less than or equal to 700. And of course, we have the non-negativity constraint because you cannot order -4 units of med A or -7 units of med B. So that's why X and Y are both greater than or equal to 0. Those are the non-negativity constraints. So now, let's see how the implementation looks like. Now you'll discover that the linprog function in scipy optimize library is actually generally a minimization thing. So whenever you are maximizing, you have to negate it. That's why when you're maximizing, you have to put the negative values. Let me put the line numbers so I can easily refer to them. Show line numbers. Good. So here now you see that we can lift the 5 and 8 directly because the linprog is actually designed for a minimization problem normally. So if you have a maximization problem, you have to negate it, and so that you cannot extract minus the negative values. But here it's just straight 5, 8. Now for the constraints, right? You see X plus Y greater than or equal to 80 is what we have here. But for proper coding for Python, right, you need to make it a less than or equal to inequality instead of a greater than or equal to inequality. And the way to do that is just multiply by -1. Inequality works such that if you negate it, the inequality changes to the other side. So if you multiply through by minus 1 now, so you have minus x minus y less than or equal to 80. So minus x minus y is less than or equal to 80. So you have minus 1 from there instead of the original 1 you should have had. But because it's a greater than inequality and you want to negate, you want to reverse it. So it becomes minus 1. Then these ones are less than or equal to inequality. So you just use them directly. So this is 1, 1, and then 5, 8. Then the next place now, that's where you put the right hand side. That's you have don't forget you've multiplied this one by minus, so it's now minus 80, 120, 700 in line 16. Then of course you talk about the bounds. The bounds are, it's non-negativity, so it can be zero or any positive value for that matter. So that's why the x bound is 0 to none, the y bound is also 0 to none. And in line 23, that's where you're actually doing the actual linear programming. Linear programming, right? That's where you're actually optimizing. So you throw in your C, then A underscore union B is your A here, and B underscore union B here is your B, this right hand side. And then you have the bounds, X bounds, Y bounds, and you're using the highs method for that. And in line 23, the work is done already. So what you're doing here is just to extract the results. So you say unit of med A now. This is just a variable name, but what it is assigned to is the result for x dot 0. That's the first result, which is for med A. So unit for med B, that's also a variable name, and it is extracting result dot x dot 1, which is the optimal number of the optimal unit for med B. And then the minimum cost, now since you are minimizing, will be result dot fun. So you are getting result from the function of the result itself. You're evaluating that. Now, if it was a maximization problem, you remember you have to put a minus sign here because this program looks like it's designed originally for minimization. So if you're maximizing, pay attention to the fact that you have to negate the values. Okay. Now, so in line 31 to 33, you're just printing out those values. So you are just saying optimum units of med A, you get the answer. That's units of med A which you have here, units med B which you have here, and then minimum cost that because that's the minimal value of the objective function. That's what is being printed here. And for the sake of plotting the feasible region, now we have lines 36 to 39. So you're doing so for the x-axis now you're doing 0 to 130. The other time I did like 0 to 140, because the biggest value on the x-axis is actually 120. So I'm doing so here it's 0 to 140 divided into 400 equal parts to make it really nice. And then y1, so here it's more like you're solving a simultaneous equation. So y1 is 80 minus x, y2 is 120 minus x. You remember now. So y is 80 minus x, y again is 120 minus x, like that. Um so you're making all the y's the subject of formula. So y1, all the y. So for the last one, right, the y, it should be 700 minus 5x divided by 8. And that's exactly what is happening here. 700 minus 5x divided by 8. So we are doing that so we can plot the feasible region. Okay. And then of course every other thing is just to get a proper plot out for that. So we have all the three regions with their assigned colors, blue, orange, green, for lines 1, 2, 3, like that. And then to fill the feasible region, you want to shade feasible region in gray color. You can shade it in whatever color. Maybe okay, we have used orange already, so let me not confuse that. Then, so you want to plot the optimal point, which we obtained as 80 by 0, and that is what lines 49 to 54 is doing, like that. And then you have the labels for the plots. So by the time you run this in one blow, you just get your results. So just like 30 seconds to 1 minute, you get your results. Yeah, that's it. So optimal solution for med A, that's 80, just like what we got manually, solving graphically. Optimum unit of med B is 0. We don't have to worry about that. The minimum cost is $400, just like we got. And this is the plot for that. This is the plot, So you have the values, you have the plots. So x plus y is greater than or equal to 80. That's the blue line. Then the orange line is x plus y less than or equal to 120. And then 5x plus 8y is less than or equal to 700 is the green line. So you can see the optimal solution is that 80 comma 0, you know, and that is what gives us $400. So that's so cool. Like Python makes things pretty easy. So you just need to understand how to translate. Know that it is originally for minimization problem. If you're maximizing, you have to negate the values. So if you have not subscribed to this channel, you can see that you'll be missing a whole lot. So subscribe right now and hit the notification bell so you can always get alerted each time a new video is released. And don't forget to comment. Let me know if you want me to teach a particular topic in mathematics and Python and all that. Or if you want me to, of course, when I talk about Python, I'm talking about maybe scientific computing or, things like this, optimization and the rest of them, basically, then you should also like and share with other people so that they can actually be part of all this great learning. Till I come your way again, keep optimizing, keep minimizing profits and minimizing cost and maximizing profits. Okay, minimize the bad things and optimize the good things, so to speak. So have a nice time. See you. Bye.